we have Professor Ram Durairajan today. He's from the University of Oregon up there. And he's going to be talking to us this week on internet data science. Want to add something, Karthik?
Thank you, Khalil.
I hope,
He's an alumnus of the IST department from the 2010 batch.
Oh,
yeah, that's more important, yes.
Okay, Ram, all yours.
All right, thank you, Khalil, and thank you, Karthik, for the introduction. It's a pleasure to be here. And good evening to all the students present. So good to see you all. Hope you had a wonderful day so far. And, so today I'm going to be talking about a couple of things, right? I mean, so initially when I tried to put this together, I wanted to talk about internet data science, but then when I conducted the pre-survey, some of you said you want to hear a bit more about other projects that we have been working in our group, as well as all the fully funded PhD positions, as well as internships in my group. So the talk, perhaps for today, as well as for the next one, is going to be as follows. I'm going to talk briefly about my background and some of my research areas of interest, specifically the problems that we have been currently working on. And then that's going to be like a bit of a teaser of the projects that we are interested in, we are pursuing in our group. Followed by that, we're going to go into a deep dive of one of the specific projects that pertains to this area of internet data science that's been really up and coming from the measurements community. And then followed by that, we're going to talk about a bit more about internships and PhD positions that you all might want to apply to down the line, or pass the word to your juniors so that they can apply as well. Okay, so let's go into the first part. So as Khalil and Karthik introduced, I'm Ram Durairajan. Please call me Ram, don't call me Professor. I am currently an assistant professor of computer sciences at the UFO, and I joined this department in 2017. And I am also the co-director of Oregon Networking Research Group. And we actually run this lab together with another professor called Professor Reza Rajai. And before joining UFO, I got both my master's as well as PhD from UW-Madison between 11 and 17. And then before that, as Karthik said, I'm from CEG, where you all are currently sitting. And I was in the IT, before IST it was called IT. So I did my bachelor's at that time. And during the course of the last 12 plus years, I've worked on a whole bunch of industry / consulting / internship opportunities. So I've worked for companies like Akamai. Some of you might know about the company. This is one of the largest content delivery networks out there. I've also worked for AT&T. Some of you might be using their mobile phones. It's a very large tier 1 internet service provider in the world. I've also worked for Accenture in the past. Currently, I am doing some consulting stuff for a couple of stealth startups out there. So overall, I've spent somewhere around 12 plus years in the area of networking in general, and I specifically focus on networked systems. How do you, connect entities together and, seamlessly make them work together? By the way, I mean, if there are questions anywhere, just, type in the chat, or feel free to unmute yourself and then, ask the question. It's okay if it is in Tamil, that's totally fine. So yeah, going back. So what motivated me to even, work in the area of network systems and, internet research in general? So when I, started my grad school, I was in this particular talk by Professor Larry Landweber. He's one of the pioneers in terms of creating the so-called autonomous systems, right? AT&T is an autonomous system. Tata Sky is an autonomous system. Bharti Airtel is an autonomous system, right? He pioneered this notion of an autonomous system back in the day when internet was in its infancy. And so he was giving a talk, and I was listening to his talk, and the first question he posed to the audience was, okay, so let's say you're traveling in an airplane, and if that airplane has certain pitfalls, let's say 1 out of the 10 times you fly in that airplane, the flight might fail. Would you use that if you knew that probability before even boarding that plane? And the answer obviously is no, because you rely on flights and the services so that you can go from A to B. If you always knew that 10% of the time flights are going to fail, you won't take it, right? And so that made me wonder, or he posed this question in a different way. Okay, would you travel in a plane that is dash as the internet that we have today? Okay, and that dash could be replaced with any metric of choice, right? Replace that dash with smart, replace that dash with resilient, or replace that with performant. One example is if somebody said, okay, if you take Indigo Airlines and it's going to take 10 days to go from Chennai to Mumbai, would you take it, right? It's not performant. You want to go from A to B in like a given amount of time. Or if somebody said, would you take this particular flight if it went from A to B, but somebody can always hack it and bring your flight down, right? So these are some of the problems that planes might have, and the same kind of problems are applicable to the internet as well. So replace that question with internet. Would you use the internet without privacy concerns in your mind, right? The answer is obviously no. So you want to fix it. So anytime you see a problem, just jump on it and fix it. So this kind of motivated me to work in this area a lot. And that's what started me to look into some of the problems. But in all truth to be told, I actually started working on computer architecture when I went to UW-Madison and I took my first course. I did not like it. It was a lot of stuff to remember. Karthik is doing a great job there. Credits to him. But I did not like that area at all. Because of all the things that I have to remember, and internet was like kind of natural to me in terms of what's happening, information flow, freedom of speech, whatnot. And so that helped me zone into my key goal, which is I want to contribute to building a more robust internet. So that's kind of the overall motivation. And so in terms of this motivation itself, I kind of like divide my problem space into two key things. The first theme is basically the idea is to just revisit some of the holy cow assumptions. When somebody said 5 years ago, here is an assumption in the internet because of which the traffic flows from A to B, I would love to really revisit that assumption and either prove that is correct or disprove that is incorrect. This is like finding new nails or new problems based on some of the old assumptions made, right? And this is exactly like that Vadivelu comedy, right? I mean, Kaya Pudichi Vidya, then he'll ask Kaya Pudichi Vidya. So I'll try to do the similar thing in my research as well. When somebody says, okay, here is an assumption, don't buy it off the bat. Just try to question yourself, is this assumption even valid? Is this assumption something that's gonna hold in many parts of the internet? And then the other interesting side of this theme is because of the fact that internet is constantly changing, it is constantly evolving, right? Back in the day, it was all PSTN, and then came your fiber, and then came your wireless. Now it's all satellite, right? There are so many new technologies that are up and coming in the internet, because of which you can ask the same question that you asked 10 years ago, but then the new technology might enable a better answer, or it can create a new hammer for you in terms of revisiting some of these old questions. So that's the other theme. So for example, if you think about programmable switches, they can enable you to, change the topology at any point of time, rather than just the forwarding behavior. So, can you come up with better defenses for network attacks, right? So that's a good example of this theme. And we'll go into, both these themes, throughout the next 4 or 5 slides when I talk about some of my ongoing research projects. But before that, I want to quickly stop and see if there are any questions in the room. Okay. All right. So again, based on student interest, so here are a bunch of projects that we have been working. So I'm going to briefly talk about these projects and then finally go into this topic of this week, Internet Data Science, which is the 4th one. And I want to segue nicely into that by talking about, what's going on in my group. So again, I'm listing all the metrics that I listed a couple of slides ago: secure, performant, resilient, smart, etc. And then, the projects that correspondingly map to each one of these metrics in terms of building towards this goal of a more robust internet. And thanks to funding agencies like National Science Foundation, ISAC, and Ripple, they have been super nice to me, giving me money to, pursue all these projects. So the first metric is secure. And, recall the the nail and the hammer analogy, right? So the new nail here is people have made assumptions about DDoS attacks. And the way this assumption has changed recently is, rather than having, just, some gigs of traffic that is unwanted going into your network, you all of a sudden have terabit DDoS, meaning you have all these attackers. They are, excuse me, constantly sending, unwanted traffic into the network. And the key, goal of, their attack is the benign users will not get access to, the resource of interest to them. Let's say this benign user is trying to watch a movie, and these attackers, they attack the server by sending unwanted traffic so that the benign user will not get access to the movie. Right. So in terms of the attack landscape, so the new nail is, the traffic is going in the order of terabits per second, rather than gigs or gigabytes of traffic per second. And the traditional defense of, the way DDoS was tackled is that people always assumed the topology to be static, right? You cannot change how the routers and the switches and the links are connected in the network, meaning if you have a mesh topology, it's always a mesh. And you cannot change the topology later in time, because of which the defense is not at all, topology aware. Right. So what we said was, okay, here is a new opportunity, and this leverages theme 2, which is the new hammer, which can enable better reconfigurable topologies. So with the help of programmable switches and programmable optics, you can change both the forwarding behavior between the switches as well as change the topology dynamically. Right. Think of this like a museum. Right. There is a big picture that a thief wants to steal. Now you're constantly changing the floor plan of the museum so that the thief would not know where to go in terms of stealing that picture, right? So that's what, that's the kind of effect that we might be able to achieve from this network. So, even though the attackers are constantly doing all sorts of, sophisticated attacks, they won't be able to, bring this server down, which means that the topology is always available for, the server is always available for the benign users, and they'll be able to stream the movie. So this is one example of a project that looks at, both new nails as well as new hammer, and kind of maps to the secure metric. Another metric that is of interest to me is performance. And typically when somebody's trying to watch a movie, there is this big lift that needs to happen behind the scenes, and that's called traffic engineering. So think of this like a bunch of policemen trying to steer the traffic in different directions so that traffic can go from A to B, right? The same thing happens in the network as well, and that's called traffic engineering. And so, network operators work on this problem all the time in terms of moving stuff from A to B. And what happened before, we looked into this problem is that people always looked at it like, okay, you want to go from A to B, just send your traffic and take the best effort model, meaning your packets can get dropped, it can get delayed, it can get altered and whatnot. And so the new thing that we said was, okay, if you know the exact routes along which you're sending the traffic, then you'll be able to do better in terms of performance, right? Think of this like Google Maps. So if I said go from Pallavaram to Gindi, right, without telling you which road to take, you might come up with a bunch of options and you might not always pick the optimal option. But then if you took Google Maps and said, okay, give me all the options, it might say what is the shortest one, which one has the least amount of traffic. If there is an accident, you might want to avoid, certain roads, etc. Right? So that's exactly the kind of, idea we are introducing here. And what is the benefit that we're going to get by bringing topology into picture? So here is a specific example. So here is something that could be applied for external disasters. So for example, what I'm showing here is sending traffic between somewhere in Georgia to the northeast up above in Boston. And when Hurricane Irene happened, right, you can always predict the trajectory of such hurricanes, and we tried to do this for Hurricane Irene. So every time the hurricane moved towards a particular link, what we did was to move the traffic away from the hurricane in a proactive fashion rather than wait for the hurricane to react. And that kind of made sure that the traffic always flow from A to B without getting impacted by such natural disasters. And here is another example between El Paso, Texas, and Jacksonville, Florida, when Hurricane Katrina happened, and we kind of did the same routing, and we tried to move around the traffic because we now know which paths are intact in the face of a hurricane. So even though the path between El Paso and Jacksonville might get affected, you can always move away by predicting the trajectory of hurricane and make your networking a bit more risk aware and bit more performant compared to what natural disasters can cause. Are there any questions? Okay, that kind of basically pointed to a bigger problem, right? I mean, we are talking about bringing performance awareness. We are looking at all these specific pointed scenarios, right? Hurricane Irene and Hurricane Katrina are a couple of examples of that. And so I was sitting back and I was having this conversation with one of the earth scientists at UFO, and he said, you know what? There are all these other disasters like earthquakes and tsunamis, and that actually causes a big havoc to people. And so I was like, yeah, people also rely on the internet. Maybe there is a correlation between disasters and the internet's robustness. So I started looking into that problem, and the new nail is people have always wondered about what happens to internet due to failures. And the failures are always assumed because of some software bug or some sort of a performance event, but there was not a big focus on natural disasters. And given that I am in Oregon, and Oregon is like a green field for natural disasters, right? We are expecting a very big earthquake in the Pacific Northwest called the Cascadia, and this is because of that subduction zone. If you guys can focus on this slide on the left side here, you see this yellow zone, right? This is the tectonic plate that's kind of moving, and when the plate releases, currently it is stuck, it's gonna unleash a massive earthquake. And the problem is, if you think about internet connectivity, it is all a bunch of wires and cables, right? So the green ones that you see here are all the submarine cables. So when this earthquake is to happen, a whole bunch of connectivity problems will arise. in the Pacific Northwest. And the problem is not just the earthquake, right? When earthquakes happen on one side, there is going to be tsunami on the other side. And this is something that we all witnessed in Chennai back in early 2000s, right? When all the Indonesian regions had earthquake, we saw, a big tsunami in Chennai beach and the coastal areas. So it's not just the, cables and the infrastructure on the spot where earthquakes are happening. On the other side, you will see tsunami. Closer to the inland area, you'll see landslides. You'll see so many such problems because of these natural disasters. And this is going to have a cascading effect, right? Earthquake happens followed by a tsunami or a landslide, right? All these problems occur back to back. And each one of these problems might affect the internet in different ways. So the question then is, okay, how can you harden the infrastructure against all these natural disasters that are impending? And the old hammer is, we have always talked about risk-aware network design. So this is an example of a, performance/risk-aware network design. So can you bring all that, idea to the table and, make this a bit more generic for different natural disasters? So that's the kind of focus here. So we have been mapping internet topology for the last 10 years and trying to figure out, where things can go wrong because of natural disasters and, what can be done to, kind of harden the infrastructure against all sorts of, natural disasters. And the final project maps to the metric smart. And this is kind of the focus that we want to be talking about for the, week, which is internet data science that specifically pertains to data-driven network management. And recall, traffic engineering is always a problem of interest for network operators. So that's the old nail. If there is a congestion event, if there is a packet loss event that happens in the internet, people want to fix it. And the key thing that is observed here is that the number of network operators who are working on the networks are, kind of a scarce resource. They are super costly and they cannot look into every such problem, right? So you need some way to, relieve the pressure from network operators and, introduce some notion of automation to network management. But the key thing about automation is that you need to know what you're exactly doing. You need to know, how to train your models. You need to know what an event is, for example. So if you're, working on a, image processing application and you're trying to figure out whether it's a cat or a dog, you have seen a whole bunch of dogs. You have seen a whole bunch of cats. So it's easy to train a machine learning model. But when you think about a DDoS attack, there is no consensus on what a DDoS attack looks like, right? People just say, hey, there is so much of traffic that's going to flow into the network and the services don't work, right? They have this vague statement about what an attack might look like. So training a machine learning model is a really, really hard problem for networking. And so is the case for congestion. So how do you define congestion in your network and, train a model? And complicating this further is the fact that even though you train a model for one network, it won't be applicable for another network because the properties of the network, in a different location is completely different. And even complicating this further is you ask that, question with that model in one location, the answer will be entirely different in another location. Let's say you search something, in Google today, you will get a different answer from what I search because things are pretty much customized, right? So this notion of developing machine learning models is always complicated because you don't have, ground truth information in terms of the event, in terms of, what you're trying to train your models for. And so the key idea that we are introducing in terms of, relieving the pressure for network operators and simultaneously bringing new ground truth to the table is to apply this idea of weak supervision. So the idea is pretty, straightforward, right? You have unlabeled data, but you come up with this whole bunch of labeling functions. So these labeling functions are given by domain experts or network operators who might say, okay, if I see 50% of packet loss in my network, chances are that it is a congestion, right? They might also say things like, if I see 80% packet loss in my network, chances are that somebody is doing a DDoS in my network, right? So based on such loose rules, you might be able to come up with a whole bunch of programs and say, okay, here is a labeling function that can capture congestion. Here is a labeling function that can capture DDoS. So what these labeling functions can enable is, these are basically noisy labels. These are not accurate. These are not really robust enough to create models, but these can somehow take you towards the direction of creating more robust models. So you can combine multiple of these labeling functions together and try to learn the agreements or disagreements across each one of these labeling functions. And so if there's an overlap between these two things, chances are that it's a problematic situation. So you do better by predicting that. But if there is a bit of a disagreement between a couple of labeling functions, then chances are that your labeling function is not doing its job, right? So based off of these labeling functions, you can then go towards a generative model that's a bit more robust compared to all the noisy labels that you have here. Now that gives you a way to encode probabilities and a way to encode confidence, right? If more labeling functions agree, you have more confidence. If less labeling functions, agree with each other, you have lesser confidence. So they can come up with a bunch of probabilities and train your discriminative model, let's say an LSTM model, to capture events of interest. So this basically helps you codify this process of coming up with some definition of what an event is, which is kind of missing in the network management research. You also come up with a way to create models to capture based on what the operators want to do, right? So this kind of opened up this new notion of network management and network operations in a smart and automated fashion, which is predominantly the focus of internet data science. Again, credits to Professor Alberto Dinotti from Georgia Tech, because he was one of those people who came up with this nice semantic relationships between different entities in the internet. So I'm going to talk about briefly in terms of different entities, and then motivate this internet data science. But before that, I'm going to briefly pause and see if there are any questions in the room here. All right. Okay. So I want to motivate this part of the talk with a specific question. How many of you guys saw PETA? Or how many of you guys are big fans of Taliban? Nobody saw PETA? Man, I was expecting a different answer, and I thought everybody would jump at it and say I'm a big Taliban fan, but that's all right. Okay, so if you are trying to watch a movie like this, right? Now, what do you think actually happens in the background, right? Think of the idea of traffic engineering. So somebody has to provision all the network for you. Somebody has to allocate enough bandwidth between the server that is owned by Netflix, as well as where your device is sitting, right? Which is either a mobile phone or a laptop. And there's all the management set of problems that needs to be handled along the way. So in the background, when you think about what happens here when this movie is kind of streamed between your device and the Netflix server, there are a whole bunch of architectural aspects that needs to happen, like, mapping the Netflix service to, specific set of organizations and users. There are all these IP addresses that are allocated. You have, geographical information, the topology is connected, right? And the content has to flow between the Netflix server and the end device, right? So in terms of, just these highlighted, ones here, these basically represent the different entities that are constantly working together just to stream this movie, right? So each one of these entities should work with each other so that you can watch this movie in your laptop or in your mobile phone from the Netflix server. So let's tease out each one of these, red entities, right? So I'm just, mapping all these entities on the table and, putting it here so that, we can do something about the semantic relationship part. So if you think about, the entities here, each one of them might have, more in-depth information in terms of what's going on, right? So for example, the IP address could be, something really specific, could be pointing to one specific address. It could be a bit more aggregate in terms of a prefix, and something like, BGP, Border Gateway Protocol, will always be using something. And this is the protocol that enables connectivity and communication between different autonomous systems. You also have all these services, right? WhatsApp, Netflix, Telegram, all these services, are going to be, mapped. You also have autonomous systems, right? Tata, Sky, Airtel, AT&T, Sprint, all these are examples. They run different protocols, and each one of them will have their own, autonomous system number. And then, within the, mapping itself, you might have different providers and they might map with each other. So the internet might have a logical topology where different autonomous systems, map with each other. And it's just a logical view of how connectivity works, but you also have the physical topology, meaning these are wires that actually make up the internet, right? How connectivity works across different regions. And what we are showing here is just a zoomed out version. And if you look at all the zoomed in versions, so here is Chicago's fiber map and how connectivity works, right? And here is Arizona, for example, and how, metro fiber deployments are happening. And so the more you zoom in, the more granularity you get, and you end up in something like this. So this is an example of a co-location facility in Seattle where, all these wires they end up in, and all your switching equipment and all your routing equipment will actually sit in these buildings, and they exchange traffic with each other. So just to pop the picture by a level, if you're trying to watch a movie, the movie has to go through each one of these entities. Your IPs have to be mapped correctly, the services have to be mapped to the IPs correctly, and then the data has to flow via each one of these wires, via these buildings, and then traffic should be exchanged and whatnot, right? Just for that movie. And think of how the internet is used today. We are not just using for movie, we are using it for e-learning, we are using it for doing all our remote work, we are using it for gaming, we are using it for so many things today, right? So for all these different applications, how is this entity relationship supporting these applications? That's the key question that you want to answer. And unless you understand the semantic relationship between each one of them, you cannot introduce better optimizations for the applications. And so if you think about internet data science as an area, right, the key focus of this particular area is that we all know some variant of relationship between each one of these entities do exist, right? So there is this connectivity from fiber optic cable to co-location facilities, and a bunch of users get traffic from those co-location facilities and whatnot. We know all that, but what this area seems to clearly look at are the following questions, right? Do we exactly know all the relationships among each one of these entities? And if so, what sort of data is actually available to talk about these relationships? Remember, you're trying to make the internet a bit smart, which means that you need to have data, you need to have information about the event so that you can train models based on the data. So data is super important about the relationships. And then once we have the data, is the data good enough? Do you have a quality data? Do you have coverage in terms of all the locations, all the possible connectivity scenarios? And is it going to incorporate, all the changes that has happened in the last 10 years in terms of new technologies? What about some of the statistical properties, right? Are there things that constantly change versus things that constantly remain the same, which are called the invariants, right? So those are all important things to understand about the data, right? So we are talking about relationship, whether they exist or not. Once we have the relationship existence, do we have some data to capture that relationship? If the data is there, now is the data good enough, right? Only then you'll be able to do some machine learning and AI on top of this data after answering all these questions to infer certain problems about application. Let's say when you're streaming the movie and you're seeing the circle of death going around and annoying you, and your video is not getting streamed. Now, how do you infer if there's a congestion along the path, right? You need to figure out an answer to all these different questions. Only then you can go answer why that congestion is happening at all. So this is the main focus of this whole notion of internet data science. So let's actually briefly look into each one of these questions one by one. So let's say, do we even know if there is a relationship among them, right? And so at a very generic view, right, when you look at all these different entities that I showed previously, and you try to come up with some entity relationship between each one of them, here's a picture of all the relationship that's going on between each one of these entities. And as you can imagine, this is a super complex entity relationship picture, right? Each one of the entities here are connected with every other entity in many different ways. So for example, your IP address is part of the autonomous system. It is also part of the logical topology. It is also part of physical topology. There is always geography associated with IP address, and users also get IP address. And of course, there are things like IP address getting mapped to services which are not shown here. But you can imagine, right? This is a super complex relationship. And this is kind of, the key focus of this area of internet measurements and modeling. They always try to infer what the relationship is between a bunch of entities and try to answer questions of interest. Right. So, these guys, they always focus on, trying to figure out the relationship, and they try to derive data about the entity relationships. And so that basically takes us to the next question or next set of questions, which is, okay, is there data? If so, how good the data is, right? And so, they do this in a piecemeal fashion. They don't look at the entire picture, but they do it one by one. So for one example of a entity relationship between users and geography is this notion of digital divide, meaning if there are, a world of users that are using the internet, how many of them, actually have proper connectivity, proper broadband, right? So for example, I heard from, some of the organizers here that people in the hostel, they are dropping, the seminar because they don't have proper internet access, right? That's a variant of digital divide because they don't have proper connectivity, right? And this is something, we studied using the maps that, we have created. And what this shows here is if you map all the county information along with the infrastructure, there are all these geographic regions, especially the Dakotas, for example, where the terrains just don't allow proper internet connectivity to be laid, because of which, the people there, they have to rely on other means of connectivity, example, satellite, right, to get connectivity. And they're always away from, better broadband connectivity. So this helps us, look into this problem of digital divide, and we were able to contribute, some data set to, map the relationship between these two entities. Similarly, there is also this relationship between geography and physical topology, right? Where is the internet cable in a particular geographic location of interest? And that is kind of what we are doing with all these mapping efforts. The one shown here is an example of that. So these are metro fiber cables at different cities in the US, and we are trying to associate geography to each one of the infrastructure entity that is out there. Another similar data set is IP geolocation, right? So many of you might have seen this in action. So for example, if you browsed something in Flipkart, let's say you wanted to buy a Ray-Ban glass, and you search it the previous night. The next morning you go to /dot, out of nowhere you see the advertisement for that Ray-Ban glass in /dot. Okay, and the way they do it is they try to figure out from where you are browsing for that particular item, and they sell the data to other websites, and they basically display the ad to you. So they are constantly keeping track of what you're doing on the internet, right? And they're trying to map the IP address from which you're browsing to the geography, and they push you content like what's happening in Eugene, for example. If I browse from Eugene, what happens in Chennai if you browse from Chennai, and the content is kind of tailored for you based on this particular entity relationship. Right, and MaxMind is a example company that does this in terms of mapping IPs to geography. And so at the outset, right, when you enter the IP address here, you will get all the information in terms of what you're doing. So this is my IP address that I basically entered, and I got the information. Even though this is I'm in Eugene, the IP addresses are bound to have some error in terms of geography. So this is actually pointing to a different county than where I am. But this kind of shows how to come up with a relationship between the IP addresses to geography. And so the question then becomes, do we know everything about each one of these relationships, right? So because we have the data now, we need to make sure the data is good enough. And so one example that I want to bring up to say that we don't know everything about this relationship is based on this farmhouse story. And this is going to be the last slide I'm going to talk about today, and we'll pick this up from the next lecture. So to show that we don't have enough information about this farmhouse, so here is a story about what happened in the US for the last 10+ years. So there was this particular house in a specific location. I'll reveal the location in like 1 minute. And there was this old couple in that house, and they're constantly being harassed by different three-lettered organizations, and they've been visited by FBI agents and tax collectors and whatnot, and police officers, for example. And they have been accused of different names, like they have been called thieves, they have been called spammers, they have been called fraudsters, right? And sometimes they have been doxed, meaning their information is actually posted on the internet. Their names, their addresses, everything has been posted on the internet by some of the vigilantes saying, hey, these are scammers in this particular location, don't go to them, right? And the funny thing is, these people are really, really, really poor people. They're not scammers, they're not thieves, they're not fraudsters. The big culprit here is IP geolocation. Okay, anytime when you query something like this, and if the data is incomplete in this particular location, it is going to give the geographic center of the country. So in this case, it's going to give the geographic center of the US, which is Kansas. a particular location in Kansas. Okay, guess what? These poor people are exactly closer to that location. So anytime when something happens somewhere in the US, and there is a fraud, or when there are events of runaway children, the IP geolocation will always point to this location, and guess what? People visit them because the IP geolocation was giving wrong values, because of which these people were called all these things when they are actually not. They are really nice people. They're a really nice couple. They actually, beyond the point, they said, what, this is too much of pain in the, neck. So we're gonna, move away from this house, right? And they finally, left that place. And all just to say, if you don't have quality data, you will make wrong inferences. And IP geolocation is like a kind of a matured field. All your advertisements today, they use IP geolocation, and it's always been around in the internet for a decade at least now, and that has this much error. Now think of all the internet data science stuff that we want to do on the network, let's say to catch DDoS or to catch congestion, right? So the problem is the data and the field is still maturing, and we don't know some of these nuances for things like these errors. So if something like this happens, how do we mitigate the error, right? We don't know an answer to that question, and that's of one of the main focuses of this area. Okay, so it's close to an hour. I'm gonna stop my talk here and see if there are any questions, and I'm gonna try to answer those questions. If there aren't any questions, I'm gonna pick it up from the next lecture, from this slide onwards, and then continue in terms of more internet data science, more into self-driving networks, and then finally talk about some of the internship and research opportunities in my group. I'll stop here. Questions?